You will find capacitors in most every electronic device that you own. Capacitors are very important to our technological society, and as such, I feel it's very important to understand how capacitors work. And it will especially be important when we start talking about circuits. Understanding how capacitors work leads to a better understanding of how certain types of circuits work. So what I've drawn here is the most basic type of capacitor. It's called a parallel plate capacitor. And it's just two plates that are attached to two wires. We don't need to worry about what the wires are connected to. We're just trying to understand how the capacitor works. And this is just empty space between the capacitors. They're not these, or I should say between the plates. These two plates are not in contact with each other. And what happens is you have an electron come down the wire and it gets deposited on the plate. And because of Coulomb's law, it's going to repel an electron off of the other plate. And that's going to leave this plate positively charged. Then another electron is going to come down the wire. It's going to be deposited down here, again because of Coulomb's law. These two repel each other, so they need to be as far apart as possible. It's going to repel another electron from this end. And we can keep doing this. We put more electrons on, and we end up repelling electrons off of the other plate. And this is what capacitors do. They separate the charge. You end up with one plate that's negatively charged and the other plate is positively charged. Now, an important quantity to understand with capacitors is capacitance. Capacitance is defined to be the charge, the magnitude of charge on one plate divided by the voltage between the plates. This is very similar to density. We said that density is the mass divided by the volume. And if you recall, when we talked about density, we said this is how you define density, but it's important to realize that the mass and the volume, these do not determine the density. The density is determined by the composition of the object, what it's made of. Here, for capacitance, it's very similar. The charge and the voltage do not determine the capacitance. It's just that this ratio can be used to determine the capacitance. This is, again, how we define it. The capacitance itself is determined by the geometry, I should say, of the capacitor and the dielectric. What is the dielectric? Well, the dielectric is whatever is between the plates. Right now I don't have anything between the plates, but whatever is between the plates is called the dielectric. So the dielectric and the geometry of the capacitor is what determines the capacitance. For a parallel plate capacitor, there's a very specific formula. This here, this K that I've written is called the dielectric constant. It's a capital K. Then we have epsilon naught, that's another constant. A, that's the area of one of the plates, divided by D, the distance between the plates. And so you can see here the geometry really does determine the capacitance. I need to know the area of the plate. If my plates are bigger, if my plates have more area, then I'm going to have more capacitance. If the distance between the plates increases, that's going to decrease the capacitance. The dielectric constant also plays a role. In other words, the dielectric matters. That's going to be directly proportional to the capacitance. In this particular case, I'm dealing with a vacuum because there's nothing between the plates. For a vacuum, it equals 1. In general, K is greater than or equal to 1. Another important property here with a capacitor, because the capacitance depends on the geometry and the dielectric, if you don't change these things, so if I don't change the area, if I don't change the distance, if I don't change my dielectric, then I don't change the capacitance. It doesn't matter if the charge and voltage change. They can change all they want for a given capacitor. That will not change the capacitance unless the dielectric, the area, or the distance between them is changing. Now, I do need to stress again, that this formula is only for parallel plate capacitor. And we're only going to be looking at parallel plate capacitors, but I want you to be aware that for different types of capacitors, there's a different formula. This one only applies to parallel plate capacitors. This formula, however, applies to any capacitor. This formula is always true. Always true. Now let's talk about the energy that is stored in a capacitor. So the formula for that is 1/2 QV. And if you've already looked at the content for this homework, you may have noticed there are two additional formulas here, two different additional relationships for the potential energy. And that actually just comes from, oops, didn't mean to do that. That just comes from this. We can rearrange this formula here, C equals Q over V. Let me do that real quick. I'll do that right here. I can rearrange that, so I've got C times V equals Q, and I can also write this as V equals Q over C. So if I take this one here and I plug it in up here, well then I'm going to get that PE equals 1/2. Instead of Q, I'm going to have CV times V, and that's going to equal 1/2 CV squared. Or I could take this one and plug it in for this. For that matter, I could plug it in here as well, but I'm going to plug it into this. So then that becomes PE equals 1/2 Q, and instead of V, I have Q over C, and that just equals Q times Q is Q squared over 2C. And so in the content, I just wrote these as all being equal to each other because they are. They're just different ways to express or calculate the potential energy. But it doesn't matter which one you use, you'll get the same answer for the potential energy. So the last thing I want to do here is just give an example of what a capacitor does, like an actual real-life kind of circuit where we use a capacitor. And this example that I give is getting a little dated, and I apologize for that. But when I was growing up, we didn't have the fancy cameras that we have today. We had the old-fashioned ones, which had a flash. And you needed that flash. And I know a lot of cameras today have the flash as well, but it works a little bit differently than the old-time ones did. So the way the flash used to work, so you have your capacitor. This is the capacitor. And what I'm drawing here is a circuit diagram. I'm trying to do my best to not make a poor one. So this is my light bulb. Okay. Well, let me draw it proper here. Okay, so let me explain what everything is in this diagram. And you're going to be seeing circuit diagrams as we continue with future units. This here is the capacitor. This is the battery. And so usually we label this would be labeled C, this would be labeled something like V naught, it's the battery. And then this is the flash. This here is the switch. And I've drawn it this way to show that it can be connected to either one, okay, and it would move accordingly. So back in the day, what would happen is, you would say it's late, it's dark out or whatnot, you want to take a picture of somebody, your family, whatever, and you're going to need to use the flash. So you had to flip the switch. In other words, what they always told us is, well, you've got to warm up the flash. The flash has to warm up. That actually isn't what happens. What actually happens in that situation is, and now let me relate this, you turn it on, and so the switch goes to here, to the battery. So it's connected like this. And actually, let me do that in a different color, just to make that a little more obvious what's happening. So the switch goes here, like that. So right now, what's happening is the capacitor is charging up. When the capacitor gets charged, then a little light would come on saying, okay, the flash is ready. And people would say, oh, now it's warmed up. Again, it's not warmed up, it's that the capacitor is charged. The capacitor is charged up. Then what happens is you take the picture, you push the button, you click, and that moves the switch over to here. Now, why is that important? Well, when the capacitor was connected to the battery, charge got separated. Now, why does the charge stay separated? It stays separated in part because of the battery. If the charge is allowed a path so that the electrons can get over, so that they can get over to these positive ones, they will take it. Okay. And that's what's happened here when the switch is flipped. Now, the charges can move around the circuit and effectively discharge the capacitor. And in doing so, they do it very quick, and so you get a high current going through the light bulb, and there's a flash. So this is one example of what we use capacitors for, and I just wanted to share that with you.